Hello everyone, welcome to the second video on feedback amplifiers wherein we are going to study the feedback concept in detail. This is the block diagram of an amplifier with feedback. Let's have a look at it. It has a signal source, comparator, basic amplifier. Now when I consider this basic amplifier, it is an amplifier which we have already studied without feedback. Then you have a sampler and you have a feedback network. When I say that there is a signal source over here, it can be either a voltage source in series with that of RS resistance, or it can be a current source in parallel with that of RS resistance. The feedback network which is present, it's a two-port network which can be built using R, L and C components, mostly R. What it does is that it converts the part of output, it gives this part of output back to the input. Okay, so the output of this particular block is given to the comparator and the input of this particular block is taken from the sampler part. Okay, now let us try to understand the sampler and the comparator in detail. This already I have discussed with you all. You can just go through it. Okay. Coming to the sampling network which is present in the output. Now it can be divided into two parts, that is voltage sampling network and current sampling network. Just have a look at these diagrams. It will be clear to you all. Now when I say voltage sampling network, I want the output voltage to be measured. And to measure the voltage, how do we measure voltages? In parallel. Okay, so if at all I'm using voltage sampling and I want to give the entire voltage as an input to the feedback network, then I will have to connect it in parallel, because we know that voltage in parallel remains the same. Coming to the current sampler, now we know that current in series remains the same. That is the reason if at all I want to feed in the entire current to my feedback network, then I will have to connect it in series. Okay, just have a look at this configuration. The current will flow, okay, to the feedback network. I hope this is clear to you all. Just like your sampling network, that is comparator or the mixer network, it is divided into two types, series mixer and shunt mixer. Now what it does is that you all know that comparator means, it literally means that it needs to compare something, right? So for the comparator block there are two inputs. Which are the two inputs? First input is the main input, okay, which is coming from the source. It can be either Vs or Is. And the second input is from the feedback network. Okay, it's basically the output of the feedback network which is given. So basically it serves like a dual input. Okay, you all have studied in LIC differential amplifiers how it works. It is a dual input, single output, which means that the output is proportional to the difference between the two inputs. Okay, that concept is being used, which serves as a mixer. Just have a look at this over here. You have two types as I mentioned earlier, series mixer and shunt mixer. Have a look at the series mixer. Now when I say series mixer, okay, we need to consider a source which is connected in series. Now this is at the input side. Sampling was something which was taking place at the output side. And how to take the output, that was shown with respect to the sampling network. Now at the comparator side, it is basically at the input side. So at the input side you should know which source is to be connected. Now when I say series mixer, series, which is the source which is connected in series? Definitely it is a voltage source. Voltage source in series with the RS resistance, as you can see over here. Okay, it's connected in series. This is a series configuration. Okay, now next it is shunt mixer. Now shunt mixer, which is the source which is connected in parallel? It is the current source. So that is the reason you have a current source in parallel with this resistance, and this also is connected in parallel with respect to the feedback network. Just have a look at this configuration over here, these two dots. Okay, it clearly tells you that it's connected in shunt. Okay, I hope this is clear to you all. Now these two things were very important for us, especially the sampling network and the comparator part of it, because depending upon these two things there are types of feedback connections or topologies. So we'll study one by one. There are 4 in total. The first one is voltage series feedback. Now, let me tell you all first only and make it very clear to you all that the first term will tell you about the output, second term will tell you about the input. Okay, the names are given that way. So, the first term is telling you about the output. Okay, so that means your output is voltage. Okay, so you can see over here in this particular configuration, if the output is voltage, you need to measure it in parallel. Okay, so you need to connect it in parallel. If at all you want to give the entire output to the feedback network, it should be connected in parallel. Okay, because we know that output in parallel, the voltage in parallel remains the same. That is the reason it is connected in parallel over here. The next thing is series. Here it was sampling network, here it was basically the starting connections about the comparator and the mixer. Okay, so when I say series mixer in the sense you should have a voltage source, which is the source which is connected in series. It is the voltage source. That is the reason you have a voltage source over here. Okay, and it is connected in series. This is your voltage series. Now have a look at this A and beta. A is equal to V out upon V in. You know that the amplifier gain is output upon input. So what is the output? V out. Input is V in and not Vs. Okay, it is V in. Similarly, you have beta. Now for beta, I mean to say the feedback network, what is the input? Input is this particular thing. Okay, and output is over here. So what is the input to this particular block? It is V out. Output of this particular block is Vf. So beta is nothing but your feedback gain, which is output upon input. So what is the output? Vf. So it is Vf upon V out, because V out is the input to this block. Let's move to the next type, that is you have voltage shunt feedback. Now again I'm telling you all, go with the words voltage shunt. So the first word I had told you all that it is telling you about the output, second word it is telling you about the input. The first word is voltage, okay, which is output. So look at the output side, output will be voltage. Okay, and how do we take voltage? In parallel. So that is the reason you have parallel over here. The second word over here is shunt. So shunt meaning you have to look at the input side now, because I have told you all first word is for output, second word is for input. So input meaning input, which is the input source which is connected in shunt, it is the current source. So that is the reason you have current source over here which is connected in shunt. Okay, you can have a look over here. Let's move to the next type, current series feedback. Again, this is output, this is input. Output is current. How do we measure current? In series. That is the reason you have series connections over here, okay, and not shunt. Okay, I hope this is clear to you. Then you have series. This is input term. Which is the source which is connected in series? It is the voltage source. So that is the reason you have voltage source over here, okay, which is connected in series. Fine. These terms again, A, beta, these are nothing but output upon input. In this case also it is output upon input everywhere. Okay, so which is the output over here? I out. Input is V in. Over here which is the output? Vf. Input I out. Okay, moving to the last part, that is, or the last type, current shunt feedback. Again, first word is current, which tells you about the output. How do we measure current? In series. So that is the reason this is connected in series. Then second term is shunt. Shunt meaning it is basically telling you about the source connected at the input. Which is the source connected in shunt at the input? It is the current source. And that is the reason you have current source over here. okay, and it is connected in shunt. I hope these 4 feedback connections are clear to you all. I expect them to draw onto your books. Okay, this is just in brief to tell you all. The first word voltage, okay, it refers to the output voltage. Okay, that is the reason it's measured in parallel or connected in parallel. Current refers to output current, so it is measured in series. Series term over here, okay, this series term, it refers to the feedback connection in series with the input. Similarly, shunt, feedback signal is connected in shunt with the input. Now with little bit more about this series feedback connection and voltage feedback connection, as we know over here, voltage feedback connection, series feedback connection, similarly current feedback connection, shunt feedback connection. Now we are going to study this a little bit in detail. Usually it has been observed that the series feedback connection tries to increase the input impedance, shunt feedback connection tries to decrease the input impedance. Similarly, voltage feedback connection tries to decrease the output impedance, current feedback connection tries to increase the output connection. Now this is what we are going to see in detail. Now this is something which we had studied in the last video also about voltage amplifier, current amplifier, transconductance amplifier and transresistance amplifier. Over here, let's have a look. Okay. Now we have to give names to this depending upon the 4 topologies. Okay. You have a voltage amplifier. Okay. Look at the output side first, because that is the first word which is going to tell you. Okay. So the first word that it tells me is about what is measured over here. It is V out. Okay. That means they have measured the output voltage. Okay. So the first word will be voltage. Fine. Then next, look at the input side. Input side, what do you find? A source which is connected in which configuration? It is the voltage source which is connected in series. So that is the reason you have series term. So this configuration, I can consider it to be a voltage series feedback. Okay, I hope this is clear to you all. Now similarly, you have over here, see, you have voltage feedback connection and a series feedback connection. Both these terms are there, right? Over here, voltage and series. Now, in case of voltage feedback connection, what it tries to do, your Z0 is going to be less and Zi is going to be more in case of series feedback. So let's have a look. For voltage amplifier, we had already found that Rin is infinity and Rout is 0 in case of ideal case, right? So Rin is infinity. Now why is Rin infinity? Again, it is made clear to you all because this is a series feedback connection. Okay. And similarly, you have Rout is equal to 0, which is less again, which clearly tells you that it's a voltage feedback connection. Okay. I hope this is clear to you all. I'm just making things clear with respect to the points which are jotted down over here. Okay. That series feedback tries to increase the input impedance, voltage feedback tries to decrease the output impedance. Shunt feedback connection tries to decrease the input impedance, and current feedback connection tries to increase the output impedance. Let's have a look at this particular thing. Okay, that is transconductance amplifier. Okay, this is a transconductance amplifier equivalent circuit. Look at the output first. What do we find over here? It is current which is flowing and we are measuring the current. Okay, so that is the reason the first term over here will be current. Look at the input side now, how it is connected, which source is connected. It is the voltage source which is supposed to be connected in series. That is the reason you have series as the second term. So I can say that this is a current series feedback configuration. Now, the very fact that it is a series feedback configuration, what have we seen over here? In case of series feedback connection, the input impedance will increase. Okay. So let's have a look over here. We had already seen this before in case of transconductance amplifier. Let's have a look at this Rin. Rin is infinity. So it's true that the input impedance increases. Now, in case of current feedback configuration, the current feedback configuration tries to increase the output impedance. That's what we have seen over here. Current feedback connection tries to increase the output impedance, and you can see over here that here R out is also infinity. Okay. This VFC and CFC, which you all can see, are voltage feedback connections and current feedback connections. Okay. So the VFC is for the over here. This is a voltage feedback connection. This is a series feedback connection as well as a voltage feedback connection. Okay. Over here, coming to current amplifier, have a look at the output. Again, that's going to tell you the first term. It is current. So that is the reason you have current. Look at the input side. It is the current source in parallel. So it's nothing but the shunt feedback. Okay. So it's a shunt feedback, and also it is a current connection. So in case of shunt feedback, what is the input impedance? It is less. Okay. Input impedance is less. See, in shunt feedback connection, Zi falls. So we have seen over here that Rin is 0. Okay. Similarly, this is also a current feedback connection. Okay, because of this. So it's a current feedback connection. So current feedback connection tries to make your output impedance more. It increases the output impedance. So we can see over here that R out is infinity. So it is clear that current feedback connection increases the output impedance. Let's have a look at the last one, that is the trans resistance amplifier. Check the output. What is measured? It's voltage which is measured. So that is the reason first term will be voltage. Look at the input side. It is nothing but a current source which is connected in parallel. So definitely it is a shunt. So it is a voltage shunt feedback connection. Now, first of all, it is a voltage feedback connection. Since it is a voltage feedback connection, definitely your Zi will be less. Let's have a look over here. So over here, voltage feedback connection, your Z0 will be less. Okay, not Zi, sorry. It is Z0 will be less. It reduces the output impedance, and also it is a shunt feedback configuration. So since it is a shunt feedback configuration, just have a look over here. Shunt feedback configuration, Zi reduces. Okay. So definitely here Rin is also 0. Both Rin and R out is 0, which clearly tells me that it's a voltage shunt feedback configuration. I hope these all 4 things are clear to you all. We try to relate the previous video with this particular concept. Fine. Okay. Next, we will see parameters of amplifiers without feedback. Okay. This terminology is very important because we are going to make use of them frequently. Transfer gain of basic amplifier without feedback is A. This is now without feedback. Okay, it is given as A. Transfer ratio or gain AV is equal to V out upon V in. Okay. See, this is the amplifier. Let us consider this particular example. This is the amplifier. Okay, don't consider this part. This is with feedback. Only this is my amplifier without feedback. So without feedback in the sense, what is the input to this? It is V in. What is the output to this? It is V out. That is the reason you have gain as V out by V in. Then next, current gain. Current gain, which you have to look at, basically the current part of it, wherein you measure the currents. Okay, so it's this particular part. You have output current, input current. So A is equal to I out by I in. Okay, that is being put up over here, AI. Okay, in case of transconductance, it is I out by V in. You can see over here, I out by V in. Okay, V in is over here and this is I out. And trans resistance Rm is equal to V out by I in. Okay, this is all A. Okay, I can say all these are A's. Fine. That is basic amplifier without feedback. Now with feedback, let me see with feedback. With feedback in the sense, I'm going to consider this entire thing. Okay, so if at all I'm considering this entire thing, let me name that transfer gain of an amplifier with feedback as AF. Fine. Now, if at all I am finding it with feedback in the sense I will have to consider this entire block. So if I consider this entire block, what is the input? Input is Vs, output is V out. So if at all I am finding the first one, that is AV, it will be AVF is equal to V out upon Vs. Okay, because you have to consider the main source now. Fine. Similarly, it goes with the current gain, I out by Is, then transconductance, I out by Vs, and finally you have transresistance V out by Is. Okay, and this all your symbols are being given F. Okay, because it is with feedback. Now, we have seen that there are two gains. One is with feedback, one is without feedback. Now what we need to do is we need to find a relation between the two. So for that we have considered this generalized diagram so that there is no confusion with respect to Vs or Is. Okay, let me consider this to be Xs. Okay, since I have considered X meaning it can be either voltage or current. Fine. Okay, rest of the things are also very clear to you all. Just see over here, this is XD. What is XD? It's nothing but the difference signal which is serving as X in, or the input signal to this basic amplifier. Output signal is named as X out, which is A times X in. How this comes? A is equal to X out upon X in. So from that you get X out as A times X in. And this is serving as an input to the feedback network. Okay, if this is the input, what is beta is equal to? Output by input. So output is XF, input is X out. So from that I can tell that XF is beta times X out. Okay, and secondly we are going to derive the expression between that shows the relation between A and AF with negative feedback. So you can see negative sign over here. Okay, there's minus. Okay, so let's start with the derivation. Okay, this theory I have already discussed with you all just now. Okay, so let's start from this difference signal. Okay, now the very fact that it's a different signal, your XD is equal to X in are gonna be, what will be the expression for this? It's quite simple. It's a difference signal. Difference between what? Between the two signals which are the inputs. Okay, so it is XS minus XF. Okay, so you have XD is equal to XS minus XF, which is nothing but Xn. Okay, so from this I can get what is XS. Okay, so it is known as the error or the comparison signal. Okay, so from this I can get XS as Xn plus XF. Okay, let me call that as equation number 1. Now the next part is about the beta over here. Okay, as I told you, beta, this is the input and this is the output. Okay, so output by input, what is the output? XF. So XF upon X out. Okay, so it is also known as reverse transmission factor or also feedback gain. Don't confuse this beta with the beta which we had studied in EDC 1 with respect to the amplifier. That is totally different. That is DC current gain. Okay, that is totally different. This is now only with respect to the feedback network that we are talking about. Okay, it can be positive or negative. It is a complex function of signal frequency. Now once you find beta, next find A. What will be A? A is something without feedback. Okay, so it is X out upon X in. So let me call it equation number 3. This as equation number 2 over here. Okay, I hope this is clear to you all. Now, just now I found transfer gain A, which is without feedback. Now what I need to do is I need to find with feedback. Okay, so to find with feedback, what I need to do is I need to consider this entire block. Okay, so if I consider this entire block, then what is the input to this particular block? It is XS. Okay, what is the output of this particular block? It is X out. Okay, so AF, that is your transfer gain with feedback, is gonna be output, that is your X out, upon input, that is XS, which we are gonna see on the next slide over here. So AF is X out upon XS. Okay, that is transfer gain with feedback. Let me call it equation number 4. Now from this equation, that is from equation 1 and 4. Now which is this equation 1? It is nothing but the difference signal equation, if at all you remember. Okay, you can go back and check. I can write this as XS I had found out as equation 1. Okay, so I can write it as, I can substitute it back, that is X in plus XF. Okay, now let me remove X in common from the denominator. If I remove X in common from the denominator, what it's going to be? 1 plus XF upon X in. Okay, now what I did is, over here I took this X in on top. Fine, I took this X in on top, and over here at the denominator side I have just multiplied it with X out upon X out. Okay, which basically is nothing but 1, right? And did that adjustment. We'll come to know why I did that adjustment in the next slide. Okay, for as of now it is the same. This X in I have taken on top. Over here you can see. Okay, and over here for this particular term I have multiplied it with X out upon X out. Okay, now let me distribute that X out. Okay, this is what I was trying to tell you all, X out upon X out. Now let me just distribute that particular X out. Okay, this X out, this X in I will move with this X out, and this X out I will move with this XF. Fine, so you get XF upon X out and X out upon X in. What is XF upon X out? Check the equation 2 and 3. You will get both the terms over here. Okay, X out upon X in is nothing but A, XF upon X out is nothing but beta. Okay, so using those equations 2 and 3, I get finally that AF is equal to A upon 1 plus beta A. Okay, which is nothing but the expression for transfer gain with feedback, with basically, to be specific, negative feedback. Okay, and for negative feedback your AF is less than A, because your denominator is going to be more. Fine, it is all. One more thing, this I should have told you all in the previous video itself, that negative feedback is also known as degenerative or inverse feedback. Okay, these are other terms, so don't get confused. Coming to the next, for negative feedback we have found out the expression. Now for positive feedback you all are going to do and send it to me. Fine, okay, this is the diagram. What will be the difference in the diagram is this, just this one sign is going to change. Fine, rest all things are going to remain the same. You all are going to find the expression for AF and send it to me. Fine, these are the references. Thank you.